Hello students, in this video we shall discuss exercise 1.1 of class 10 maths. Now this chapter is based on the Euclid's division algorithm. So let's see, first see the division algorithm. What is the division algorithm? When you carry out a division, we get the four parts of a division. See, dividend, divisor, quotient and remainder. We know all this, and the relation among them is there. Dividend is equal to divisor into quotient plus remainder. This is called the division algorithm. So Euclid's division algorithm is like, if a and b are two positive integers, then there exists another integers q and r such that a equal to bq plus r, where r is greater than or equal to 0 and less than b. So this is you see, a is the dividend, divisor b and quotient q, and r is the remainder. And when in every division, when you carry out a division, the remainder is always greater than or equal to 0. It may be 0. If exactly divisible, then it is 0. Otherwise it will be greater than 0. The remainder can never be less than 0. That means we cannot get any negative integer, negative number in the remainder. So this is the for this condition we have to write r is greater than r, means remainder is greater than or equal to 0, but less than b. B is the divisor, and you carry out all the divisor and you just notice it, always the remainder is always less than the divisor in every division. Always the remainder will be less than the divisor. So this condition we must mention along with this Euclid's division algorithm. Actually it is totally Euclid's division algorithm. You can get in your book also. So now we have to use in exercise 1.1. you see. Now using Euclid's division algorithm, we have to find the highest common factor HCF of the given numbers. So first let me show the first. There are two numbers given, 135 and 225. So two numbers are given. So in earlier classes we have done the HCF by long division method. You can remember, if two numbers are given, then we started the dividing the larger number by smaller number this way. I'm just doing, just recalling this system. 225, now divide. Alright, then again divide the previous divisor by this remainder 135. Again by this remainder we have to divide the just previous divisor, previous divisor of the step, divisor of the step. Now it is 2 times. So now it has become 0. When we get the 0 in this step, the divisor is the required HCF. When we get the 0 in this step, with the divisor of this step is the required highest common factor. This is the long division method you have already done in the previous classes. So this is, we are applying this Euclid's division algorithm. We are applying Euclid's division algorithm in the same process to find the HCF. Just applying Euclid's division algorithm. So first you see, first we have done this part. What we have divided, we have to write solution by Euclid's division algorithm. So first this is the dividend in the first step. Dividend is 225, so 225 equal to divisor is 135 into quotient 1 plus remainder is 90. All right, in the next step, just we shall show this stepwise. This division we just split it and show the stepwise. Next 135, and in this step the divisor is 90, quotient is 1 and remainder is 45. In the next step, dividend is 90, remainder is 45, quotient 2 and remainder is 0. Now in this case, this divisor is the required HCF, therefore required HCF equal to 45. That's all. So you can in this way you can do the rest of the sums of number 1. Then let's see the number 2. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 and or 6q plus 5, where q is some integer. So this sum also we shall use the Euclid's division algorithm. So here you note that in the question you are asked show that any positive odd integer. So by Euclid's division algorithm, we shall consider a equal to 6q. Here we must consider 6 as the divisor, 6q plus r, and condition will be r is greater than or equal to 0, and here divisor is 6, so it is less than 6. So therefore what will be the value of r? First 0, because r is greater than or equal to 0. Next 1, 2, 3, 4 and up to 5. 6 will not be there because less than 6. These are the values of r. Now if r equal to 0, then value of a will be 6q. Now 6q we can write 2 into 3q. Now see, if any number has a factor 2, then it is never odd, it is an even number, which is even. If r equal to 1, then a equal to 6q plus 1, which is odd, because it has no factor to as 2. There is no 2 factor is there. If r equal to 2, then a equal to 6q plus 2. This we can write 2 into 3q plus 1. So it has a factor 2, which is even. If r equal to 3, a equal to 6q plus 3, which is odd. If r equal to 4, then a equal to 6q plus 4, which is even. If r equal to 5, a equal to 6q plus 5, which is odd. Now we are asked in the question that we have to show that positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 4. Now see, positive odd integers are there. This one is odd, this one is odd. Now see, odd is 6, first one is 6 plus 1, 6 plus 3 and 6 plus 5. So now in the last line you can write, hence any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. This way you can show this. Next, number 4. I am showing the number 4. See, use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So here hint is also given. Let x be any positive integer, then it is of the form 3q plus 1, 3q plus 2 or 3q plus 1 or 3q plus 2. Anyway, so now note that to show the square of any positive integer, we have to find the square and we have to show the square of the positive integer. So same way we can write by Euclid's division algorithm. A equal to, here we shall consider 3 as the value of b. 3q plus r, where r greater than or equal to 0 and less than 3, as we consider 3. Therefore r equal to 0, 1, 2, because r is less than 3, so we can go up to 2. So there are 3 values of r. If r equal to 0, then a equal to 3q definitely. But we have to find the square of the positive integers. So value of s square will be 3q whole square. So it is actually 9q square. Alright. And this one we can write 3 into 3q square. So 3m, where m equal to 3q square. Because m is a positive integer. It is so some integer. So it is given in the question, it is some integer. So this is also an integer. Already we have defined, and it is defined in the Euclid's division algorithm. So in place of 3q square we have we can write another integer. It is m. Next, if r equal to 1, then a equal to 3q plus 1. Therefore a square 3q plus 1 whole square. Now use the formula of the whole square. A plus b whole square, it is a square plus 2 into a into b plus b square. Simply, so it is 9q square plus 6q plus 1. So we can take the common from these two terms. We can take 3 simply. So 3q square plus 2q. Now this is of the form, we can write 3m plus 1. This is also integer. Operation of integers are also in integers. Integers are closed under addition, subtraction, etc. So here, where m equal to this. If r equal to 2, then a equal to 3q plus 2. Therefore a square equal to 3q plus 2 whole square. So a square plus 2 into a into b plus b square. Now 3q already we have shown 3q plus 1 and last one is 3q plus 3m or 3m plus 1, 3m or 3m plus 1. Now this we we need to rearrange this in order to bring this form. 12q plus this 4, we have to write 3 plus 1. Just I have split this number 4 and written the sum of as a sum of 3 and 1. Now we can take the 3 we can take 3 common from these 3 terms. So this way, why I have done this, to bring the form 3m plus 1. We have to show the 3m plus 1. So this is also an integer. We can write 3m plus 1. Alright. So now we have shown that the square of the positive integers is of the form 3m plus 1 and 3m plus 1. This line you can write as the square Alright, next. Next I'm showing the number 5, you see. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. Now this time we have to show the cube of the positive integers. Again, by Euclid's division algorithm, a equal to 3 cube plus r, where r is greater than or equal to 0, less than 3. Therefore r equal to 0, 1, 2. This the value of b is 3. We have considered the value of b is 3 here. So if r equal to 0, then a equal to 3 cube. Therefore value of a cube will be 27 q cube. Now we have to show, you see in the book, we have to show this positive cube, the positive integer is of the form 9m plus 1 or 9m plus 8. So this we can write 9 into 3q cube. So therefore we can write 9m, where m equal to this, because this is also an integer. If r equal to 1, then a equal to 3 cube plus 1. Therefore a cube. So we have to find the whole thing cube. Now use the formula of whole thing cube, a plus b whole thing cube. It is a cube plus 3a square b plus 3ab square plus b cube. Now we can take 9 common from these three terms. Take 9 common. So this is of the form 9m plus 1. Last one, if r equal to 2, then a equal to 3 cube plus 2. Therefore a cube equal to 3 cube plus 2 whole thing cube. Now again use the formula a cube plus 3 square b is 3 into ab square plus b cube. Now take n9 common. So 9m plus 8, where m equal to 3q cube plus 6q square plus 4q. Now see, these are the forms of 9m, 9m plus and 9m plus 8. That's it.